Can you hear me?
Hello.
How are you?
Fine, fine. And you?
Yes, everything is fine. Welcome to our seminar.
Yeah, thank you very much. Now it seems the microphone can work, and can you hear my voice?
Yes, it's fine.
Okay,
Very good.
Then may I test the screen?
Yes, of course. Share screen qiling, Rahimjon.
Yeah, it seems okay.
It seems okay. Oh, okay.
Yeah, you can see the screen.
Yes.
Okay, okay,
Yes.
then that's okay. Still 5 minutes?
Yes, we have 5 minutes. We just wait for others to come in. How's the weather in Japan?
Typically rainy season.
Oh, I see.
Not so hot, more lower than 30 degrees Celsius, but very humid.
How about coronavirus? How about coronavirus?
Stabilized and more or less normalized life.
Okay. Many things forbidden nowadays because of coronavirus in Japan, like flying abroad.
Yes, especially going out of Japan and entrance to Japan. Still, there is some limitation.
Yeah. Here,
But
Professor Arsen Vladimirovich Pshu, he's also now joining us.
Good afternoon, dear friends. Добрый день.
Hello. I'm Yamamoto.
Yeah.
Assalamu
This is our chair, Shavkat Alimov. Yes, this is Alimov.
Nice to meet you.
Yeah.
I'm not sure what to say. Good morning or good evening.
Good evening. Now 8 p.m.
Professor Ashurov, it's early morning. For you, it's good evening. It's better to say it's good day.
Very good time. Plus 4 hours advancing.
Are you ready? And the demonstration is given to you. Yeah.
Yes. And then I'm very sorry. Just say 1 minute for completing a couple of cafe.
Yeah. Okay. Добрый день, Арсен Владимирович.
Здравствуйте, Шавкат Александрович. Здравствуйте.
У вас сейчас уже утро, да?
И у нас 2 часа дня, без 4 минут 2.
Да, у вас же московское время, да?
Да.
Понятно. А погода у вас тоже ничего?
Немножко вот затянуло, как бы дождь собирается, а так уже тепло, 30 градусов бывает.
Вы знаете, удивительно, здесь то же самое, 30 градусов. Хотя в это время в прошлом году было уже 40.
Ну, немножко запаздывает лето, да.
Это видно из-за глобального потепления. В этом году прохладнее.
Да.
Тут какие-то бывают неожиданные эффекты.
Здравствуйте.
Так. О, здравствуйте, Мурат, как у вас дела?
Здравствуйте, Мурат.
Хорошо, все, спасибо большое. Здравствуйте, Рафан.
Да.
Здравствуйте.
Так, у нас еще 2,5 минуты, по-моему, да?
Да.
Тут трудно подсчитывать. Так, похоже, что докладчик будет делать доклад из своего кабинета.
Да, у них же вечер сейчас. У нас 4 часа, а в Токио сейчас 8 часов вечера.
8 да?
часов вечера. Да, 8 вечера. 4 часа впереди они.
Да. Он же в университете Токио.
Вот здесь участвует Холмат. Он член-корреспондент Академии наук России. Сейчас, вот, он наш студент нашего университета, сейчас член-корреспондент Академии наук России, работает в Новосибирске.
То есть это где-то посередине между Токио и Ташкентом, да?
Да. А сколько времени, Холмат?
6
вечера, да.
Так и есть, точно посередине, да?
Да.
Да, получается.
Я удивлялся, что раньше разница с Токио у нас была всего 3 часа, сейчас 4. Я удивлялся, вроде так далеко Токио. Yes. Okay.
Okay, we can start, Shakatarjan.
Yes.
Okay, maybe can I share the screen?
Yeah, Professor Yamamoto. Now let me introduce to our
Thank you very much.
participant. Yeah, just a moment. I want to introduce Professor Yamamoto here.
Yeah.
So Professor Yamamoto, he is associate professor of Tokyo University, and he has his master's degree in 1983 from Tokyo University, and he received PhD from the same university in March 1988. He is editor of many journals, mathematical journals, in particular Journal of Inverse and Ill-Post Problems, and Nonlinear Functional Analysis and Applications, and many others. And he is fellow of Institute of Physics, Great Britain, executive committee member of Inverse Problems International Association, honorary professor of East China Institute of Technology, advisor of Institute of Applied Mechanics, Ho Chi Minh City, Vietnam. So let's welcome Professor Yamamoto in our seminar. Please, Yamamoto, you can start
Thank
now.
you very much. Okay, I would like to share the screen. Yeah, I hope that you can see the screen, maybe a little bit bigger size. Oh, I hope that the size is fine to everybody.
Yeah, it is fine, yeah.
Fine. Okay, then first of all, I would like to thank Professor Ashurov for inviting me to this weekly seminar. It's my great pleasure and honor. And especially it's my great pleasure to give a talk about fractional calculus and the fractional differential equations, because at your seminar, there are many excellent specialists working in this field many years. And I myself belong maybe to the young generation for this field. My career for this field is more or less 10 years or 12 years. Anyway, you are more familiar with this field. Okay, then today's talk is, I think, in a sense, not very new, but my purpose is give some convenient framework for long-standing research field, fractional calculus and time fractional differential equations. I don't insist that my method is absolutely best way. I don't mean so, but I hope that my framework provides you some convenient frameworks. Then please let me start. Then several parts are divided. Then in principle, today's talk is based on my published paper. And later on, I can give the information, but that paper one can find in archive, or I have revised. Then finally, if you are interested and you in keeping the revised version, gradually I will send the PDF file. But anyway, then the numbering and the sections are just the same as that published paper. Then part one is the usual introduction. By the way, I don't know usual way, but I think if you have any questions and objections, please stop my talk to ask and give your comments. Okay, then the first part is introduction. Then very roughly speaking, our target, our objectives are very classical, and the Gilbertian Kaput derivative, and for example, given by this, the order alpha is just for simplicity is between 0 and 1, and that is a first target. And the second is also with respect to consider.
Professor Yamamoto, I'm sorry.
Yes.
I just want to say to organizers of this seminar, please start recording.
Oh yeah. Okay.
Raham John, start recording.
I should
Are
do
you
something?
listening me? No, you are not. This
Okay,
moderator,
then I can wait.
Raham John. Oh, okay. Thank you.
It's okay.
I'm sorry. But yes, it's fine.
Do you think that I should repeat from the beginning?
No, it's okay. Everything fine.
That's okay.
No.
Okay, then I will continue. Then also would like to consider some linear or semi-linear diffusion, time fractional diffusion equation in a bounded domain, and also simultaneously ordinary differential equation, so-called initial value problem for time fractional ordinary differential equation. Those are very rough description of our research objectives. Okay. Then we will use the following notation. I think more or less traditional, and the Dirichlet-Kaput derivative is given by this, but I'm very sorry, I will skip index 0, because always we consider from t equals 0. Of course, we can generalize, but we will skip sub-index 0. Then Riemann-Liouville derivative is like that. Then fractional integral operator, I prefer to use J, not I, but in some major references, I alpha, but please let me use J alpha. Okay, I think the notations are more or less standard. Then maybe I will skip this. Okay, then one thing I would like to call your attention. Dirichlet-Kaput derivative at first, okay, V at first one-time derivative. Then applying fractional integral operator, which is say 1 minus alpha times the integration. Then eventually plus and minus, then alpha times derivative. That is very clear. And Riemann-Liouville is the opposite, namely at first 1 minus alpha times the integral, then one-time derivative. Then Dirichlet-Kaput derivative is widely used, of course, but this order may cause some complexity, namely at first derivative, then after that integration. Therefore, some regularity balancing is a bit delicate. If V is not differentiable, then this is something a motivation for my talk. Therefore, if we consider V is not one-time differentiable, some interpretation is necessary for that. Maybe one is like a distribution sense or something. Then, of course, there are many previous and outstanding approaches. But anyway, that is more or less a starting point. Okay. Then, illustrating example is as follows. Let me consider very simple ordinary time fractional equation, but that is very simple. Then we will put initial value. Then very well-known solution formula is read as follows: Vt equal A plus, this is nothing but the integration, alpha times. Then that solution formula is very well-known, and of course, for example, in my one of my favorite books by Cubas, Sylvester Trujillo, it is written and T alpha times F in a continuous function, then this can make sense, justified. Then
maybe there is F instead of V under the integral.
Thank you. F, thank you very much. That must be F. I'm very sorry, that is F. Then let us test, thank you so much. And let us test a very concrete function, say power gamma. In principle, we will consider L1 function. In L1 function, then gamma must be, can be assumed to be greater than -1. Then we can substitute this function, then this is a concrete form. Then this condition corresponds to this one. Gamma is greater than -alpha. Then, of course, by the general theory or this concrete calculation, this formula is justified. But other cases, yeah, more or less delicacy happens. Then we would like to consider uniformly all the situations. This is a purpose, roughly speaking. Okay, then I will skip that. Well, and also I would like to call your attention. Also, we would like to consider by the physical reason some singular source term. This comes from, say, I think quite practical situation, namely source term is like impulsive. In the very short moment, putting some force or something like a distribution input. Then what will happen in the solution? Anyway, those issues, then that is a motivation. Then our strategy is extension of the operator, derivation coupled to derivative. Extension means that we want to extend the domain where derivative is defined. And of course, this is not a unique way. Other way is possible. And one major way, that variational formulation. And also there are many distinguished results. But here we are concentrating on extension of the operator. How to extend the domain of this operator. Okay. Then now the main part, now we can proceed. Then extension of fractional derivatives. Then the extension will be done in 2 steps. Then the first step is within positive order of Sobolev spaces. Okay. Then some preparation or introduction of notations. Then J alpha. Also, sorry, this may be not so conventional use of the letters, but please let me use J alpha is like a integral fractional integral operator starting from 0. Then J sub alpha is opposite or something like a conjugate to this. Then, of course, this means alpha is positive. Then we will define it for L1 function, but for some reason, please let me start L2 space. Then alpha equals 0 for convenience of the notation, J0 alpha equals 0, J sub 0. This is identity operator. Then in principle, we will consider for the moment L2 space. Also L1 space can make sense this, but please, anyway, formally speaking, L2 space we will consider. This means that this is a domain of J alpha. We will consider J alpha for L2 function. Then that is directly approved, like the semi-group property. Then also, this is not explicitly used, but the operator, but the tau is very simple operator exchanging 0 to capital T. And thanks to this operator, the properties of the space only for related to J alpha is sufficient, because J sub alpha is the operator after exchanging 0 and capital T. Thanks to this translation or exchange or reflection operator. Therefore, I will not touch the details of the proof, but in principle, the arguments can be sufficient to be done only 0 to small t. Then after that, we will operate tau, then we can derive corresponding result related to J sub alpha. That is a small remark. Then also, please let me use this kind of notation, 0C1. This means that one-time continuously differentiable functions satisfying at t equals 0, v vanishes. This is the notation. Then exchanging by tau, 0C1 means that just exchanging roles, capital T and 0. Then this means that v capital T equals 0. But this C1 class. The next is H super alpha denotes, say here is between 0 and 1. This denotes Sobolev-Slobodetsky space. Then the norm is defined. I think that is quite a standard definition. Then this is, please remember that H super alpha. This is a classical Sobolev-Slobodetsky space. Then we need more spaces, namely H sub alpha, not super alpha. H super alpha is Sobolev-Slobodetsky space, but H sub alpha is denoted, defined by closure of 0C1 by H alpha Sobolev-Slobodetsky norm. this means that more or less natural definition, namely, this means that at t equals 0 vanishing functions, then we will extend such a C1 function vanishing t equals 0 is extended by H alpha node, taking the closure. Then maybe the choice of the notation could be improved, but please still use alpha H is like a corresponding closure, named 0 C1. This means that capital T vanishing. Then we will take the closure in Sobolev-Slobodetsky node. Then for the unification of the notation H0 and also this sense 0 is set as L2 space. This is a preparation for the function space for the first step of the extension. Then H alpha, H sub super alpha is Sobolev-Slobodetsky space. Then H sub alpha is like a closure attaching t equals 0 or vanishing condition. Then we can give the characterization in terms of the Sobolev-Slobodetsky norm, but this is not very important for the moment. Therefore, I will skip that. By the way, after my talk, according to your wish, I can give this PDF file on my presentation, which is almost same from the published paper. But anyway, please let me proceed. Then first result, the proportion to the numbering is say that corresponding from the published paper for your convenient reference, maybe later on. Then proportion 2 is the range of Riemann-Liouville fractional integral operator. Then J alpha is, we will fix domain L2. Then the range is exactly H sub alpha. H sub alpha is a closure of the 0C1 some space by the Sobolev-Slobodetsky norm. We can prove that is surjective operator J alpha to H sub alpha. Then thanks to this, just for exercise or example, if one wants to verify some function is H sub alpha, then by the definition, not directly checking the Sobolev-Slobodetsky norm, usually it is a bit more complicated. From the opposite side, namely, if we can find J alpha L2 function equal T beta, then this means that T beta is H sub alpha by the surjectivity. Then in this case, yeah, one can prove rather, one can verify this inclusion rather directly. Now the definition of the derivative, fractional derivative, say for the moment I must use the new notation. Then say round dt alpha is defined as the inverse to J alpha. Always J alpha should be considered as the operator from L2 to H sub alpha. Then this is a definition. Then anyway, the point is that fractional derivative in our work is always defined by the inverse of integral operator by attaching the range of integral operator. Therefore, in this case, the domain of our time fractional derivative is range of J alpha. Then that is more or less automatic definition. Of course, we must exploit the property, but anyway, that is the definition. Then by the proposition, previous proposition, this is just equivalent statement, namely, our fractional derivative gives the equivalent norm L2 between H sub alpha. And that is also more or less automatic conclusion from the definition. Okay, once again, that is the most important key. namely fractional derivative is just defined it very simply as by the inverse of J alpha. Then J alpha inverse, then henceforth, please let me write J minus alpha. I hope not so complicated. Then next step, maybe natural to extend the order alpha is greater than 1, but more or less by the way as you can expect. Therefore, also later on I will not use so much during my talk. Therefore, maybe I will skip. But this is more or less common idea. Namely, if alpha is greater than 1, we will compose natural number part plus the say fractional part, sigma is between 0 and 1, and then we can repeat similar procedures, but I will skip that. Okay, then definition is the same. Then after that, eventually we can define fractional derivative for all non-negative order. Alpha beta is greater than or equal to 0. Then by the definition, the proof is not absolutely trivial, but not so complicated on the basis of the first proposition. Then alpha times derivative is defined it H alpha plus beta. Then range is, that is surjective. Range is H beta, of course, very natural, minus alpha order. Alpha order missing, then H beta. And J alpha is vice versa. Then this is a bit intermediate result, but this is like the composition of derivative and the integral operator, but more or less semi-group like property. Okay, then that is the, okay. Then of course now we extend it, but needless to say, we must relate our derivative with the classical derivatives, fractional derivatives. Then we will not use this fact, but we can prove our extended time fractional derivative is a minimum closed extension of Dirichlet Kaput derivative, defined it 0C1. This is a C1 class, but vanishing at t equals 0. Then closed extension. Roughly speaking, this means that, oh, sorry, this is the typo. Okay, our derivative, sorry, this our derivative, round T alpha, is a near friend or a relative of Dirichlet Kaput derivative, because closed extension, but minimum. Therefore, the properties are more or less inherited from the Dirichlet Kaput derivative. Then first remark is that if alpha is greater than 1/2, more or less this is in any case Soboledsky subspace. Therefore, by the Sobolev embedding, if alpha is greater than 1/2, of course V is embedded in continuous function. Then V0 can be verified to 0. Then relation our derivative with other classical derivatives. If starting domain, all derivatives are same. That is very natural. Then H sub alpha is in H sub alpha, our derivative coincides with Riemann-Liouville derivative. Therefore, our extension is not so extravagant. Anyway, then now we have extended Dirichlet Kaput derivative to H sub alpha. Then next, we would like to extend more to negative order. Then once here is just the J sub alpha, then starting from 0. Yeah, I think this is not so important. Then similarly, we can prove that J sub alpha. So far, mainly we have considered J super alpha, but J sub alpha also the same property, beta H to alpha plus beta. Yeah, isomorphism. Then how to extend J alpha. The main idea is just the adjoint or dual operator. Also, that part is more or less automatic and the abstract. And anyway, then the way is as follows. We will use so-called Gelfand triple. This is the general explanation. We will prepare two Hilbert spaces, V Hilbert subspace of Hilbert space X. Then embedding is assumed to be continuous and the dense in X topology. Then X is Hilbert space. Then we can identify the dual space of X is itself X prime X. With that identification, we will consider dual space V prime. Then this is so-called Gelfand triple. V prime is the dual space of V. Under the convention that X prime is the same as X. Then that is very common way for defining a negative order Sobolev space, especially without boundary condition. But here we will consider more or less.
Instead of H, maybe there will be X, no? V is a part of H.
Oh, sorry.
X, yeah? This triple, triple.
Thank you very much.
Yeah, okay.
That is X, not H. Sorry. Yeah, thank you so much.
Okay.
Then if this apply Gelfand triple to alpha H, then we can get this triple. This is the dual space of alpha H. Okay. I did not explain the H alpha as the Hilbert space, but the natural way we can define a scalar product and to be a Hilbert space. Okay. Then like that once again. Then once simple remark is that if alpha is greater than 1/2, L1 is embedded minus alpha. The proof is very simple. Okay. Then the next is also general knowledge from the functional analysis, namely extension by dual. Then that is very fundamental definition, namely capital K is a bounded operator from Hilbert space X to another Hilbert space Y. Defined it over X. Then we define dual operator of K prime. K prime is defined by from Y prime to X prime as the maximum operator satisfying to this. That is duality pairing. Okay, then X is capital X. Yeah, that is very standard definition of the dual operator. Then dual operator always keeps maximum operator satisfying this property. Then let us test our operator J sub alpha. Already I have explained that J sub alpha is isomorphism beta H to H alpha plus beta. Then at first we apply so-called closed range theorem. This is from the general theorem. J alpha prime can be proved to be isomorphism from this dual space to this dual space, namely that. That is a first fact. Then second fact, we can prove directly if VW both are L2 function, L2 scalar product, J super alpha V and W is same this. This is a second fact. Then how to relate J alpha prime? J alpha prime is the maximal operator. Then this and this maximality of J alpha prime, automatically J alpha prime is greater than this is J super alpha, that J super alpha, also the typo. Then this is the definition J alpha prime, then this is the extension of J super alpha. Then the next is the definition is now simple. Okay, okay. Then the also we can prove by that definition. Sorry, I forgot. Okay, Okay. Then we define alpha derivative is the inverse J alpha prime. And please notice that J alpha prime is extension of J super alpha. This means that this definition still can extend the previous fractional derivative. Then we can prove the following isomorphism. Namely, if the index is minus, then range of this is this one. Then the range is minus alpha minus beta. Then if H beta as the domain, then the range, if beta is bigger than alpha, here is the positive part, H sub beta minus alpha. But negative dual space, like that. Then this is also natural consequence of that. And so far, somebody feel that everything is abstract and everything is just formal. Then I must fill up the contents in this abstract definition. Then first interested that some examples of the calculations. So far, do you have any questions?
Oh, no, please continue.
Okay. Then
you will give some
yeah.
examples.
Yeah, now I will give some examples. Then those examples can support that this kind of definition can be natural extension. Then the first proposition is maybe looks very trivial. This is our extension of J alpha. This extension coincides L1 space, namely just concretely written, this one. And of course, the point of my approach is operator theory, then fixing the domain of the operator, then extension. Therefore, if one will neglect those procedures, and if one will see this, oh, that is very, very trivial. Yeah, in a sense, yes. But J alpha prime is defined it through the dual operator attached with the domain. In this case, the domain can be wider operator. But if J alpha prime is restricted to L1 space, this is nothing but the classical integral operator. But yeah, but so far it looks very, very trivial. But the proof is not so complicated. But one must prove. Then, but the proof is just by typical density argument by approximating. Then I will skip that. Then other thing is that since taking the inverse, we can reach the time fractional derivative within our framework. Therefore, also L1 function. This is our definition. L1 function we can get, and this means that more precisely, this should be considered in the distribution sense, C0 infinity prime. Okay, then still you feel that the result looks trivial, but please look at example 3. Then let us consider, okay, alpha is between 0 and 1. Then we will consider this kind of singular function. Then in our sense, this put the fractional derivative. Then the result is Dirac delta function. Okay, here, to be sure, this is L1 function, just L1. But L1 is embedded into some negative Sobolev space. Then we can operate this. Then the result is Dirac delta function. Therefore, some cases, our fractional derivative can work for more singular function. Okay, then here is more say tempered function. also this is like a fractional derivative of the so-called the heavy side function. Anyway, then I will skip the basic property coming from the fractional calculus, but maybe one thing I would like to call your attention. Since our fractional derivative is attached with a domain, roughly speaking, like that. Roughly speaking, this comes from at the t equals 0 vanishing function. Therefore, thanks to that boundary condition, always successive derivatives just alpha plus beta. If V is assumed this space that I would like to repeat that more or less corresponds that D0 equals 0. In general, of course, this equality does not is not correct. And the proof is not so complicated, but I will skip, and also some formula of the Laplace transform. Of course, according to your wish, I can give this PDF file. Okay, then now please let me proceed. Time fractional ordinary differential equations. Now we have extended fractional derivative even in some weaker Sobolev space. Of course, this is not only theoretical interest, but also.
Excuse me, before going to part 3.
Okay.
What is the derivative of constant in your definition?
Okay, then the constant case. Okay. In one word, the same Riemann-Liouville.
Okay, it's not 0, right?
No.
Oh, okay.
And the reason is that if we consider positive order, the function must be in H alpha, but the constant function does not vanish at t equals 0. Therefore, we can, okay, maybe just one explanation. Sorry. At first, several times, even I was confused. Okay, somewhere. Okay, maybe I missed it, but they say L1 function, our derivative coincides with a Riemann-Liouville derivative.
Okay.
L1 case. Yeah, I forgot the proposition number. Yeah, thank you so much for your question. Yeah, not here. Yeah, this one. Yeah, that is Riemann-Liouville. Then
Okay.
that is our derivative. Yes. Okay. Now I can proceed the next part. Then that is shortly I would like to treat time fractional ordinary differential equation. Then I think also we need to prepare a Mittelwerfer function, but I think quite well known, and also we will not use explicitly these formulas, but that is very convenient for solution formula. But anyway, I will skip that. Okay, then let us start initial value problems. Then of course there are diversity of the formulations for initial value problems. Then but according to our derivative, let us adopt this kind of formulation. This is very the equation, very simple linear time fractional equation, but the point is that formulation of that part. Then just by the audience kindly asked the question, roughly speaking, this derivative L1 function is the same Riemann-Liouville derivative if u minus a is in L1. Therefore, this formulation itself looks very, very traditional for the Riemann-Liouville time fractional ordinary differential equation. But the small difference that we will consider our extended derivative can be operated even to the distribution. Okay, then u minus a, this means that h sub alpha, like that. Yes, for the moment, F is in L2 function. That is fundamental formulation. Yeah, do you have any questions?
Yes, so it's not necessary to add to the right-hand side of the derivative dt alpha from the constant A, because it's not zero, yeah?
No, because
in this case, u minus A will be on the right-hand side minus lambda u minus A, no?
No, here is u. Yeah, of course, you can change u minus A by replacing F is F minus A.
Yeah,
but
because it means that
the essence is that, yeah.
When t is 0, u is equals A, yes?
No, because u minus A is must belong to the domain of H alpha. This,
yeah.
This
it means that HR. It means that u from 0 equals A, because u minus A is 0, no? It's the definition of H alpha.
Okay, then alpha is
if alpha is greater than 1/2, in this case u minus A is continuous, and at the point 0 it's 0.
0, yes, but the derivative of A is not 0.
Yes, but u minus A is 0, and u on the right hand side u is not 0. Yeah. Okay. Thank you.
Yes. Yeah. I think equivalent reformulation is possible, but for uniformity, please let me write that. Then, just as I said, that this corresponds to this kind of notation. Then I think not so bad way. Anyway, then for the moment, let us proceed with this notation. And just for making sure, this is not same derivative of u. U minus A derivative is not same derivative of u, because this is more or less similar to Riemann-Liouville.
Yes. If you suppose that u minus A belongs to H alpha, sub alpha, it means that u minus A, u equals A, okay?
Yeah, okay, yeah. But the alpha is
when alpha is greater than 1/2.
Yeah, that case is a difference, but alpha is smaller than 1/2, no difference.
Yes.
Yeah.
Thank you.
Therefore, yeah, thank you very much. That is an important point and a bit confusing. Okay, then solution formula by our framework, we can write that, but essentially, this is the same formula as you can understand, but our case in some subscribed space. Yeah. Okay, but that is not so new, and also the same treatment is done for multi-term time-fractional ordinary differential equation. Then next, let us consider more singular non-homogeneous term. Say f is minus alpha. Then this is the same. Then f is not L2 function, but minus alpha. Then this is the same formulation. Then our case, not H sub alpha, but L2 function. Then at first, unique existence. That's okay. Unique existence, the proof is the same, thanks to our extended derivative. In this case, this derivative is defined for all L2 functions, but the range is H minus alpha. Then with naturally expected a priori estimate. Then one motivation of that, we will already, as I mentioned, that we would like to consider this kind of impulsive source function. Then that case, this is a special case, minus alpha, but must be greater than 1/2. Then this case, by the solution formula, extended the solution formula, we can represent the solution like that, and justified within our framework of the time fractional derivative. Okay. Then also maybe I'll skip. Then maybe that's enough as the example for ordinary time fractional differential equation. Then next, that's the second last part. Initial boundary value problems for fractional diffusion equation. Then bit more about we will consider omega is a bounded domain. We will not consider whole domain like a Cauchy problem. Always for uniformity, we will consider initial value boundary value problem. Then minus A is a regular elliptic operator. We need not symmetry, but we need some regularity. And just for simplicity, this is not essential, but for simple description, please let me assume that zeroth order term is non-negative. Sorry, non-positive, negative, sorry, negative. Then we will attach conormal derivative. Then H1 omega is a blah, 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 etc. is denotes a usual over space. Then our basic formulation of initial value boundary value problems is as follows. This is the same. Then U minus A should be in H sub alpha. Then that is elliptic part in spatial direction and F. Then we will consider zero Dirichlet or zero Neumann condition. Also, we can consider so-called the Robin. The existence, unique existence of the solution in this class, U minus A is H alpha, U itself, X direction H2. Then similarly, we can prove the unique existence of the weak solution, but here initial value is just L2. F is L2 in T, but X direction H minus 1. Then we can prove. Then the proof is done by say Gariokin methods, especially if the coefficients are time dependent. But this is not the main central interest of this talk. Then just I would like to remark that anyway, we can prove unique existence of the solution within this class. Then please let me proceed. Maybe also this is skip. Then now, as a consequence of within our framework, I would like to demonstrate one result for improved regularity. Improved regularity. Okay, that is our basic formulation. Then here, F is just L2 function, L2 in T, L2 in omega. Then A is say some H10 or something like that. Then one interest is that if F is more regular in X and or T, how much we can improve the regularity of U. That is improved regularity issue. Therefore, at first, let us assume that F is more regular in time direction. Then that is the main result. Oh, then assumption is that F is H beta, H sub beta. But unfortunately, unlike usual partial differential equation, only regularity in time t of F does not produce. Then the condition is that F minus A is an elliptic operator, small a is initial value. F minus AA should be in H beta. Then we can proportionally improve the time regularity. Say if beta equals 0 is the fundamental result, L2 case, then L2, H2, and H alpha, L2. That is the standard regularity. But if we assume more regularity in time t, but minus capital AA, then we can lift up uniformly by beta. Then, of course, this assumption is troublesome because if beta is greater than 1/2, this implies that f minus AA must be 0 at t equals 0. Therefore, this looks very strong condition if you will compare with the heat equation. But that is essential. Okay, this is not diffusion equation, but ordinary differential equation. Namely, let us consider very simple ordinary fractional differential equation. Then here it's anyway constant function. Then of course this f is C infinity, very smooth. Okay, initial value is 0. But then we can write down the solution. But of course, T alpha is not C infinity. That is very clear. Namely, twice alpha derivative is T minus alpha. Then this is not in L2 space. This difference comes from this function is not H beta or H alpha because that is constant function. Therefore, for improving the regularity in time t, capital F is not only regular in time, but also some compatibility condition with the initial value is necessary. Then just the naive remark is as follows. Sorry, this is very simple ordinary differential equation, but needless to say, if F is C infinity, then okay, U is C infinity, but let us consider fractional derivative. Then this is a notational things, but H infinity means that the intersection. Then F is C infinity from 0 to T, close the interval does not imply C infinity. But H infinity 0 T imply also the solution is H infinity. But if F is C0 infinity, that's okay, C infinity, but never C0 infinity. Then if C infinity close the interval, we can prove that semi-open interval C infinity. But this means that those can be directly verified. But anyway, T equals 0 always is a delicate point for the regularity. Anyway, of course, the one additional interest is that what will happen not only for simple equation, but for diffusion equation, what will happen at the singularity or regularity at the t equals 0 according to the regularity of non-homogeneous term. But maybe this is a completely different story. Okay, then the proof is skipped now. I think maybe 5 minutes. I can.
Yeah, we have 9 minutes.
9 minutes. Okay, thank you very much. Then next, opposite direction. Namely, now we if non-homogeneous term is less regular in time, then what will happen? The solution. Namely, we will consider this. But F is not L2, but minus alpha H, blah, blah, blah. Already we have considered this situation for ordinary fractional differential equation, but now we will consider fractional diffusion equation. Then always the motivation is that some impulsive source term. Then only as for the unique well-posedness of this corresponding solution space L2 and the U itself minus alpha H. The solution in time is not so regular, just minus alpha H. Then we can prove the unique existence. And the proof is, as usual, not trivial, but rather simple on the basis of the definition of the our time fractional derivative. Now, those are more or less basic part of the theory, just well-posedness, just to say qualitative properties. Also, I skipped the asymptotic behaviors, but however, my specialty is inverse problems. Therefore, quickly, I would like to touch some other topics the one is very simple inverse problem, and also I will touch a very recent work with Yuri Ruchko. But anyway, the first is inverse problem. Then only one example I would like to show, demonstrate. Then the very simple inverse source problem, namely omega is a bounded domain, but the spatial dimension is 1, 2, 3 for simplicity. Then x0 is some interior point fixed. Then f is continuous function on closure of omega. Then, but the t function is not necessary in L2 function. Then by the previous basic unique existence result, sorry, we will consider this initial value boundary value problem. This means that initial value can be zero, is zero, so it's zero. But that is no homogeneous term, but mu t is minus alpha a, h. Then here is a typical source term modeled in practice. Namely, this is like a source of the contaminants. Then fx is a spatial distribution of contaminants. Mu t is the time change of the source terms. I have been working simulation of after the catastrophe of nuclear power plant in 2011. Then this case, at first, the modeling of the contaminant source like that is very important. And especially if the catastrophe is very short time, mu t is more or less impulsive function, like a Dirac delta, or the support is very, very small function. But anyway, this is like a mathematical formulation of the inverse source problem, and sometimes related to very serious social problems. Anyway, then mu t, our case is linear combination of Dirac delta functions, for example, here. Then our interest is that fx is given. We know where the contaminant source is, but we want to know how to change in time, namely the determination of mu t within impulsive source functions. Then our observational data is at one monitoring, 1 point x0. Then the uniqueness, if we assume that if x0 is not 0, then uniqueness is proved. Then proof is actually very simple, because if mu is unknown function is assumed to in L2, already that is well-known result. Therefore, the proof itself just changing improved the regularity of mu to L2. But this can be done by operating J alpha prime. That's all. Of course, J alpha prime is injective. Then the proof is just a few lines. Okay, maybe I just let's part quickly. I'd like to mention that very new results under processing with Professor Ruchko. Then we will consider semi-linear equation. That is a semi-linear term. Then the Neumann boundary condition. And we assume some assumption F, semi-linear term. Roughly speaking, semi-linear term is local Lipschitz continuous and some boundedness in some Sobolev space. Then this class, of course, restrictive for semi-linear term F, but rather wide semi-linear terms can be included. We need not global Lipschitz stability. This means that a coefficient can depend M. Oh, this is, like that, yes. Then comparison principle is just production of maximum principle. Then the main result is as follows. Of course, that is a semi-linear equation. Therefore, we cannot prove in general for all T unique existence. Therefore, we must, in general, limit it to local existence in time T. Say T0 is small or big, but dependent on the some norm or initial value. Okay, then we will consider this class of the solution. This is the same, also this is the same, but we can prove continuity at t equals 0. Okay, then that is the main result. Namely, that is semilinear term. Semilinear term is F1, F2, this ordering, also the same ordering between initial values. But then order preserving. Then this solution coming A1, F1 is greater than or equal to the second one. Then that is very useful for giving upper or lower bounds, and also can produce global existence in time t for semilinear equation. Then key idea is extremum principle for derivation Caputo derivative, proved by Luchko 2009. But this kind of regularity is necessary. But our solution class is weaker. Therefore, thanks to the well-podness arguments, we must at first approximate our solution by sufficiently smooth solution, which can admit extremum principle, this kind of irregularity. But those arguments can be done smoothly, rather smoothly within the framework of that our fractional derivative. Now, concluding remark that many works should be or can be done in the near future, including inverse problems, also the optimal control problem. Then application weaker solution is quite often preferable. Then naturally, understanding of the fractional derivative in corresponding weaker sense is needed. Then our approach is more or less on the basis of the operator theory. Then this means that parallel to the semi-group theory by maybe say, yeah, Sobolevsky or Japanese school. Then additional information on that, as I already said, that the source paper, but not including the final part of comparison principle, was published in Open Journal Mathematics or found archive, but I have revised. Then if you are interested in revised version, please send the request to this address. Then very gladly I will send the revised file of this article. Now the time is coming. Then thank you very, very much for your kind attention. Thank you so much.
Thank you very much, Professor. Really, it was very interesting. Any questions? Maybe some comments. It really was very interesting, and especially the last part with examples for elliptic operators. But it seems to me that it's necessary to assume that this operator A is positive, no? Because of that,
this is not necessary. No, this is not necessary.
Not necessary, yeah. It's enough that coefficient C is less. There is only one condition for coefficient C, yeah, in the previous examples, not here.
Okay, yeah, but for simplicity, I assume maybe the beginning diffusion equation.
And no additional assumptions about the coefficients B. It's very interesting because of B, it's not self-adjoint. And yeah. But it's not positive because of B. If B are not identically zero.
No. But yeah, but the point is that the key for the corresponding argument is as follows. Of course, if BK is 0 and C is say negative, I think no problem. Yeah?
Yes.
Then, but here is lower order term. Therefore, we can regard this is as a non-homogeneous term. Then we will apply something like an iteration scheme or fixed point theorem. Therefore, yeah.
Thank you very much.
Therefore, we can compensate. Yeah.
Yeah, really, it's very interesting, and the proof will be very interesting. Yeah. You said that we can find it here in internet. Yeah.
Добрый день, коллеги. Я уж по-русски говорю. Добрый день, Шавкат Арифджанович.
Здравствуйте, Камил.
Да. Это спросите, пожалуйста, я вот английский это не знаю, вот где обратная задача. Он ищет там, у него было видеопроизведение, там μ на f. Пусть вот этот плакат вернет.
Can you show the inverse problem when the right-hand side is mu multiplied by f?
Yeah, just a moment, I will shift. Sorry. This one, yeah?
Да.
Так.
Вот у него есть условия, видимо, он ищет функцию u и μ от t, да?
Нет, только mu.
Μ ищет тогда обратно.
Ну, естественно, но в общем здесь главное найти mu.
Да, μ. Вот это условие f от x ноликом, у него, видимо, и некое достаточное условие. А вот если это условие нарушается, что-нибудь у них известно или нет?
Just a second.
Yeah.
About the conditions of f. Are they necessary or no?
Pardon? The condition of
about
f?
the additional conditions for the function f of x.
Okay, then the at first regularity and in this
you have some. Yes, f of x 0 is not 0.
Not 0. This means that observation point must be in the support of the source term.
Yes, it's
Support.
sufficient, yeah, to solve the these inverse problems. Ваш вопрос, Камил Сабирович.
Вот если вот это условие нарушено,
тогда...
Yeah.
If f of x 0 equals 0.
0, yeah. Then indeed the statement is not so complete. Okay, then
в этом случае задача проще.
Then we can relax this condition much weaker, namely f does not identically vanish.
Чтобы f тождественно не равнялось нулю.
Ну, там, понимаете, какая, если вот мы берем уравнение без дробных производных, обычно, скажем, для вот параболического уравнения возьмем, это условие, оно существенное, поэтому, если это нарушается, там единственность теряется, строится контрпример.
This condition is very interesting because in case when alpha is 1, in case of parabolic equation, it's very important.
Yes,
is it important in this case too?
Yeah. And the sorry, maybe my preparation is lazy. This theorem, the assumption is not at all the best possible. That is very, very strong.
Okay. Ну, здесь
спасибо, ладно, там уж понятно это.
Thank you very much.
Ну вот еще раз, Шавкат Арифджан, вопрос. Есть ли какие-то случаи, вот все-таки такая некая общая теория строится, вот примеры, где все-таки эти решения вот для дробного производства строятся в явном виде? Есть такие красивые примеры, что есть явное решение?
When you just can show us the solution as some well-known function in special cases, maybe.
Sorry, for the inverse problem, or
can you give the examples where the solution is some elementary function or some special function, which is well known? Some special cases.
For the initial value problem?
You gave, I remember you gave this example when it's t in the power alpha minus 1 divided by gamma.
Okay, yeah.
Something like that.
Not this one. Maybe this is
вот, например, внизу, да, вот эти примеры, видите, especially example 3, it's a delta function.
Ну, это не пример решения задач, конечно. Ну, ладно,
но
понятно.
если дельта функция с правой части, то возникает вот такое решение, значит. Частный случай.
Сейчас, ну да, ну так.
Thank you very much.
And please understand that this is our derivative, not the Riemann derivative.
Yeah. More questions? Есть еще вопросы?
Спасибо.
Пожалуйста.
Спасибо.
Аригато. Аригато гозаимашита.
Как Ташкент поживает там, Шавкат Валерьевич? Какие новости у вас?
Есть еще вопросы? More questions or some remarks? Professor Umarov, do you have some questions?
Thank you. Yes, I have one question.
Yeah.
Please. Yeah. You're very welcome.
Can you go back to slides where you described the isomorphisms?
Isomorphism. Yeah. Okay.
Yeah.
I
I apologize. Exactly the time I got, I lost connection. So, nevertheless, yes. Yes, when you define your fractional derivative using isomorphisms.
Yes, over integral operator. Yeah.
Yeah. My question is the following: you are using heavily Hilbert structure. L2
yes. Of course. Here, definitely L2 space. Yeah, Hilbert.
Well, if you use instead of Hilbert structure, Banach structure, for example, LP, LQ.
LP, and the
what happens in this case?
Okay, that is very sharp and very essential question. There are several already works. Then always easiest work is the work done by myself. Then I have created one preprint for LP space, namely P is greater than 1. I don't remember P can be 1 or not, but anyway, at least P is greater than 1. One can do similar, but unfortunately, it seems that still open problem, namely alpha plus beta, but here not beta, beta minus epsilon. Epsilon cannot be 0, unfortunately. Then this can be proved by usually by integral operator. Then after that, taking the inverse operator. But some part of the result, for example, can be found in nice lecture note in mathematics from Springer by Gorenflo and Bestseller. But I have continued the calculation. Then even in the lecture note by Gorenflo Bestseller, some epsilon gap, namely beta minus epsilon, but also other references I found epsilon gap. Then if you can tell me your email address, gladly I will send the related materials, including my preprint, which can be found in archive. But that's the situation. Unfortunately, not perfect isomorphism.
Well, may I ask this question, Professor Yamamoto?
Yes, please.
Yeah, you say that H beta minus epsilon when you are considering LP spaces.
LP.
Does this epsilon depend somehow on P or not?
But no, epsilon can be arbitrarily small.
For any P, it is just arbitrarily small.
Yes,
is that right?
For any fixed P, epsilon can be arbitrarily small, but never 0.
Okay, thank you.
Then in some estimates, one must take care integration 1 over T. But if epsilon gap, then that is integrable. This is the main reason.
Thank you very much. More questions?
No.
By the way, for your convenience of the audience, I will send some related works to Professor Ashurov. Then that is not secret material. Therefore, say if you are more interested, if you can contact Professor Ashurov, then Professor Ashurov, please forward the material.
Okay, thank you. Thank you.
Thank you.
You're very welcome.
In this case, I would like to express my gratitude on behalf of the participants of our seminar. Thank you very much. Domo arigato. Best wishes to you. Best wishes. Bye.
Thank you so much.
Thank you.
Thank you so much for everybody. Have a nice evening.
Have a nice day.
Bye.
Thank you for everybody. Goodbye.